All right, so we're starting Unit 6. Unit 6 is all about means. I mean like averages. We're not in proportions anymore. So that means we're going to do a couple things differently. In Unit 5, it was all about, we were trying to figure out what's the true proportion. We didn't know, so we were making all our guesses based on this sample proportion. Remember, these are parameters. Sorry, I'm writing over my own writing. These are parameters, and these things are statistics. Parameters are truth, right, absolute certainty, and we rarely know what that is. Statistics are guesses based on data. Okay, that was all about Unit 5. Unit 6, we're going to be doing things a little differently. This time I want to know about mu. This is the Greek letter mu. It's not an M, it's not a W. It's like a U with a little like tail thing. Okay? So that represents the true mean, the true average. We don't know what that is, so we estimate it with X bar. Very much involved with the mean is the standard deviation. We don't often know the true value sigma, so we estimate it with the sample standard deviation S. So same ideas. We want to know truth parameters. We don't know these two things, so we make guesses with our statistics, X bar and S. Because there are two things that we don't know, that we're estimating, we actually can't use the normal model anymore. What? No. We have to use something a little bit different. So new model, very similar. It's called the t-distribution, or the t-model. So you'll notice this t-model is the solid line. That's what it says there. It's this solid line. The dotted line you see there is the normal. So it's really similar, just has a little bit fatter tails. So what you read here is we can't use that 68, 95, 90, 99.7% rule. But everything else we do works very similarly. Very much the same. Okay, so slightly different. Please read your book about the t-model. Great story in there about the man who discovered the t-distribution. He worked making beer. Good story. You should read it. All right, so other than that, things work pretty much the same. So we're actually going to just jump in and do a story problem so you can see what's the same and what's different. So here's our problem. A coffee machine dispenses coffee into paper cups. You're supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup. That shouldn't be a big surprise. Some are going to be a little bit under, some are going to be a little bit over. Hopefully not too far over, or your cup will overflow. Below are the amounts measured in a random sample of 20 cups. Okay, so it is a random sample, and we're looking at 20 different cups. You will also notice that a lot of times in our stories, we have really small sample sizes, okay, and it's small. That's another reason why we end up using this t-distribution. It just works better for small samples. So we're going to create and interpret a 95% confidence interval for the mean amount of coffee. Okay, we're thinking average amount of coffee dispensed from the machine. And then we're going to come back to see if a mean of 10 is reasonable based on this data. So the first thing that you should do is take this data and put it into your calculator. So remember, we do that by going to Stat and Enter. We get our different lists. You'll see I've already put mine in list 6. You can use, of course, whichever list you like. So take a minute and make sure you have all that data in your calculator. It's going to be very helpful for us. All right. So the first thing that we do for confidence interval is check conditions. No big surprise there. First condition is the same. Is it random? We get to write yes. It says so in the problem. All right, so that's given. Like check, we're good to go. The next condition that you may or may not remember from Unit 5 was that n, remember this is our sample size, that's 20, is less than 10% of the population. True story, nobody checks this one. So you can like cross it out. You really don't have to do it. The sample sizes are so small that it's pretty much always true and nobody bothers. No, I'm not going to get you in trouble. Nobody checks this one. On the AP rubrics, this one does not show up when it comes to means. The next one in Unit 5 was about NP hat and NQ hat. But we don't have, okay, remember, right? We had NP hat and NQ hat. They had to be greater than or equal to 10. But we don't have P hats anymore. We're talking about means now. So like this puppy is gone. We're going to replace it with something else. And that something else is nearly normal. Okay, whoa, Ms. Kersh, you wrote a lot. Yeah, I did. In order for us to use the t-distribution, which is really close to normal, our data needs to be normal. That goes back to this idea of sampling distribution, which we learned about in Chapter 18. So in order for a lot of these assumptions to work and kind of the building blocks that we have, our data needs to be normal. So if you have a really small sample, like 15 or less-ish, the data really should look like a normal model. What do I mean? I mean like when you graph it, like you should see a normal model. If you have something that's kind of moderate sized, it doesn't need to be perfectly normal. We're just going for unimodal, symmetric, normal-ish. And if it's a large sample size, remember we had that central limit theorem? Ooh, you might need to go back, review. Central limit theorem says if your sample size is large enough, the sampling distribution will always look normal. So if you have a big sample, like, it doesn't matter what the data looks like. You'll be good to go anyway. But you do need to be able to explain why, thinking in terms of the central limit theorem. Maybe think back to that applet that I used where it would drop the different items, create a mean, and it ended up looking like the normal model. That was not a good normal model. All right, so maybe remind me, we can look at that again. All right, so let's go ahead and check our conditions for this story. All right, so we already verified that we had a random sample. Okay, like, right, I wrote that up here, check. We need to verify that it's nearly normal. We do that by actually graphing this data. Okay, so in my calculator, I'm going to go to stat plot, and I'm going to change my graph so that I'm selecting a histogram. Okay, that's what I'm going to check to see if it looks nearly normal. My data is in list 6, and I will do a zoom 9 to get a histogram. Okay, remember my sample size was 20, and so I'm looking for something that is symmetric and unimodal. Okay, now this one's sticking up just a little bit high, but you know, for the most part, you can see, right, unimodal, more or less symmetric. That's pretty good. Pretty good. We'll take it. We'll take it. It's pretty good. So on your actual assignment, when it comes to discussing nearly normal, you would actually sketch that graph. I'm going to have to pull mine up so I can, look at it. So I don't know, something like this. Okay. And I would say, yeah, it's symmetric and unimodal. So I'm good to go. Notice this is not a work of art. It is a quick sketch. Quick sketch is all. All right, so we have checked our conditions. Okay, 2 big conditions we're checking, random, nearly normal. Step 2 is our mechanics. So back in Unit 5, we had this p hat plus or minus our z star times that standard error formula. Remember, this puppy comes from your pink formula page. So we're just going to swap some things around. Instead of p hat, I'm using x bar. It's still a statistic. Instead of v star, we're going to use t star because we're using this t distribution. Looks a whole lot like the normal. And then, instead of this square root p hat q hat over n, I have this s over square root of n. This is also on your pink formula page, listed under means. Pretty convenient. some of you might have noticed that I put this interesting little thing right here that says DF. DF stands for degrees of freedom. There is only one normal model, but it turns out there's actually quite a few different T models. And so we have this little subscript called the degrees of freedom that tells us which one you were using. Okay. Kind of weird, but we'll go with it. All right, so in order for me to plug this stuff in, I'm going to need my calculator. All right, so the easiest way to do this is to let your calculator do the confidence interval for you. So I'm going to scroll over to tests, and we are doing, let's see, an interval. I'm going to scroll down to the intervals. Oh, we're doing a T interval. Okay. Like, notice it's a 2-sample T interval. That's not us because we don't have 2 samples. It's not a Z interval. We're using T. So I'm going to use this option that says T interval. Now, what I have highlighted right here, it's flashing here. Okay, flashing here. It says stats. That would be if you were already given an X bar and an S and a sample size to plug in. But we actually have a list of data. So I'm going to scroll over and highlight data to say, hey, I have all the data in the calculator. As a matter of fact, it's in list 6. C level would be your confidence level. And I'll go ahead and push calculate. Pretty cool. It has everything we need, including the answer and how to show our work. So I have this X bar, the S, and the N that I can plug in to my formula. So that's what I'm going to do. Where it says X bar, I get that from my calculator. Okay? It said 9.845 plus or minus. This thing we could come up with just like we came up with our Z star. But I'm going to teach you a little secret. You can actually just write T star as long as you fill in your degrees of freedom. Degrees of freedom are equal to N minus 1. Pretty cool. So we had 20 as our sample size minus 1. It means I write a little subscript 19 right here. And that's good enough. I fill in my S, that was in the calculator, over the square root of 20. And I'm just going to copy the interval straight over from my calculator. Why? Because we spent a whole unit learning how this works. I trust you now. You know how it works. Let's do it faster. Okay, let's just copy it down. As long as you typed it in right, as long as you copy down right, you're going to be safe and good to go. All right, so believe it or not, this is all the work that you need. It's pretty cool. All right, the last step is our conclusion. Notice this is very similar to what we did in Unit 5. I am 95% confident that I could put in the word true right here. That would be cool. Instead of proportion, I said mean, because now we're talking about means. The mean amount of coffee dispensed by this machine is between, and then I just pull out the numbers from my answer, 9.752 and 9.938, and that's in ounces. Unit of measure is going to be important. That's my interval. So the question is the claim of 10 ounces reasonable? Well, no. As a matter of fact, I'm 95% confident that on average, this machine fills up between 9.7 ounces and 9.9 ounces. 10 is not in the interval. I don't know. I'm thinking maybe I should call up this coffee company, complain that I want my money back because they're underfilling my coffee. On average, it looks like the highest it's going to go is 9.9. Okay, now maybe you're like, Ms. Curtis, come on, 0.1 ounce, not worth suing over. Okay, maybe. But I still think that they have some false advertising going on right here if they're claiming 10. So please notice how many things are very similar to what we did in the last unit.